So thanks, it's an honor to be here. So this is joint work. This is joint work with Emil Fels, who's a postdoc at Technion, and Lisa Hartung from Mainz, who was a PhD student here. Okay, I'm going to talk about Gaussian free field on the tree subject to a hard world. Okay, so let me start with some notation. It's going to be very simple. It's going to be on the tree. I'll try to motivate it. It comes from planar domains, and I'll say something about it very soon. But let me take some notation. So you have a binary tree. I'll call 0 the root. The leaves denoted by Ln. X is the depth of a vertex, and x minimum with y is going to be the common, deepest common ancestor of x and y. And now I'm assigning IID Gaussians to all the edges of the tree, and then I define a field which is indexed by, so the random function indexed by the vertices of the tree, and h of x is going to be just the sum of the edges of these Gaussians on the edges leading from the root to the tree. So this is, okay, I'm sure most people, all people here now, recognize this as the branching random walk with, okay, so this can be viewed as a branching random walk with binary branching and Gaussian steps, by which I mean you place a particle at 0, and then each particle splits into 2, each of the descendants, each of the children takes a step according to a Gaussian, to a centered Gaussian, and then repeats the process of splitting and having kids taking steps. And this is okay. And you can view, in this case, hx is the position of particle x in this genealogy tree. And it's easy to see you're summing Gaussian, so hx is just a Gaussian, a centered Gaussian with variance equal to the depth of x. And the covariance between hx and hy is just the length of the common path to x and y from the root, and that's given by the depth of the common ancestor, or alternatively this form. And okay, and I'm going to be interested in the following event. So what happens if you take a subset of your graph of this tree, D, and condition it to be, require it to be positive, which I'll denote by omega plus D. Often I'll take Ln, the entire set of leaves, so I'll condition require the leaves to be positive. You can say everything that I say here essentially holds if you require the whole field to be positive, not just the leaves, just somehow more customary. And I'm going to be interested in two questions. The main question is going to be how does H behave if you can condition the leaves of the tree to be positive. As a kind of a side product, I'll also get sharp asymptotics for this probability. It's kind of, you can imagine that you need to understand this in order to analyze this. But again, this is kind of the main interest. And let me talk about motivation. So if you write explicitly the density of this branching random walk, so you get something like this. This is kind of a Gibbs formulation. So this means just IID Gaussians on the edges. And then, okay, so this is the density. 1 over z is just a normalizing constant. And then this is the density with respect to which measure. Well, okay, so at the root, I'm pinning it to be 0, so this is the 0 boundary conditions. And everywhere else, the reference measure is Lebesgue, which you can write more economically as just minus 1/2 of the gradient on the tree. So T is the tree of Motettos. And if you think about it, if you look at it this way, this is just an instance of a discrete Gaussian free field with the particular choice of graph being the tree, then of the n, and boundary conditions 0 at the root. And of course, the more interesting case is the planar case, of which I drew a picture, where you replace Tn by some scaled up version of a domain V, scaled up and discretized version, and you put boundary conditions, say, at the boundary of your domain. You think of this domain as just being the box, the unit box. So if you scale it, it becomes Vm. So so this is kind of a picture. That's the field. And again, the interesting question is what happens when you condition this field to be positive in some subset of the domain. And this has been, okay, that's kind of what I said here. Okay, so if you put Vn, that's what you get. Okay, and DGFF is just kind of a canonical case of general gradient fields known by the name of Ginsburg-Landau. Okay, you can think of, I mean, the Gaussian free field is, okay, I don't need to somehow motivate this audience, but yet a Gaussian free field, discrete Gaussian free field can model various things. In particular, it can model an interface between two phases, say liquid and gas of some particular substance, where you have coexistence of these two phases. So it's often used as kind of an effective interface, and then the positivity requirement has a physical interpretation. Okay, I want this interface to be positive in some part of my domain. For instance, if it's indeed kind of liquid and gas of a given material, substance, then maybe it's the container in which this thing is found. Well, it's a container, so the interface cannot go below the bottom of the container, and so you have positivity. And so this question comes from physics in the planar case, and it's a kind of an important question in physics to understand what happens when you condition the field to be positive. And it indeed has been kind of studied very extensively in the 90s, and mostly in the 90s, maybe early 2000. And there are known results for the planar case. And maybe the one of the prominent results is by Bolthausen, Deutschel, and Giacomin, which says the following. So if you take a subset of your continuum domain, say the unit box, so I have some subset of the unit box, which is kind of compactly embedded, and I discretize it as well. And now I require the field to be positive in this subset of the domain. Then there are first order asymptotics, well derived in this paper, and okay, so that just says that the probability decays exponentially as log n squared, n being the diameter, the scale parameter, times the explicit constant. G is just a constant, just 2 over pi, and the capacity of U with respect to V. Okay, so this comes from harmonic analysis. It's not so important, but it's the minimal, so the Dirichlet energy, the minimal Dirichlet energy of a function that goes from 0 on the boundary of V to being 1 on U. So you want to find a function that minimizes the Dirichlet energy, and the requirement is this function is 0 on the boundary of V. So this is in the continuum, and 1 at U. So kind of like the most economical way to go from U to V in Dirichlet energy, and we'll get to this constant later. Moreover, they use this to show that the field, once you condition the field to be positive on UN, it in fact becomes much higher. So you condition it just to be positive on UN, and what happens is that it actually goes to level 2 square root of G log n, in the sense that it's okay. So it's tight after division by log n. It's tight around 2, or it converges if you want in probability after dividing by log n to 2 square root of G. So 2 square root of G log n plus little o of log n in probability at every uniformly all vertices on UN. So it lifts. So you condition the field to be positive, and it lifts dramatically to 2 square root of G log n. This effect is known as entropic repulsion, and it's the same thing you see in random walk. If you take a random walk and condition it to be positive, it actually goes to the order of square root of n at distance n, or at time n. In fact, the planar Gaussian free field is just a surface analog of random walk. So it's somehow not too surprising. Why this particular 2 square root of G log n? Well, the proof. This is how the proof goes. In fact, the proof shows that the minimum of the field unconstrained, so without the positivity condition, if you just look at the field, at the minimum of the field at the, at the subset where you want it to be positive, so typically it's minus 2 square root of G log n. So if in the previous picture, the typical minimum at the subset is minus 2 square root of G log n. And so what the field does is actually lifts at that region exactly by the order of the minimum, thereby making the new minimum positive. Okay. So that's really it turns out this is the most effective way for the field to be positive. And okay, this is kind of a seminal paper that started the whole business of among other things, started the whole business of minimum and maximum of Gaussian free field. And the point is that now we know much more than just this. So in fact, we know a lot about the maximum and the minimum. In particular, we know that if you take the maximum or the minimum, the field is symmetric, and you subtract. So we know that the minimum or the maximum. I'll talk about the maximum because then I'll avoid using a minus sign. So in fact, not only that maximum is on first order 2 square root of G log n, but in fact actually it has this logical correction, and if you subtract, then you get convergence to the usual randomly shifted Gumbel, and we've seen in the previous talk that this is kind of a universal feature that holds for many other logarithmically correlated fields with just the rate of the Gumbel changing and this random shift. Okay, so we know more. And we know the extremal process, tail asymptotics. We know a lot about the field, and so the hope is that we can use this new technology that we have, or new knowledge, to kind of improve upon these results, which are essentially, the state of the art, as far as I know. Well, there's a bit of additional work by Yehuda, but more or less this is kind of the state, as far as I know, the state of the art. Okay, so this work on the, okay. Sorry, let me just say one more thing. Okay, so the idea is that to use new knowledge to kind of study this, revisit this problem of hard wall on the planar domain, but I'm not doing this on a planar domain, I'm doing this on a tree. Why? Okay, so why the tree? Well, the tree is kind of a toy model of the planes. For the sake of Gaussian free field, extremal theory, extreme value theory, the tree and the plane are not that different. And you can see this by just looking at the covariance structure, so both of them are Gaussian. If you look at the Gaussian free field, the discrete Gaussian free field, in the bulk, the variance is G log n, and the covariance, well, it's a logarithmically correlated field, so the covariance decays as log of the distance between x and y. If you compare this, okay, so the tree, we've seen that the variance is n, and the covariance decays like 1/2 the distance between x and y. And okay, I claim these two things. I mean, if you replace log n by the depth, so you can think of this, or you can think of n being the diameter of the model. So here the diameter is n of the underlying graph. Here the diameter is n, and here the diameter is maybe 2n. And so 2 to the n. Sorry, 2 times 2 to the n. And so this is just log of the diameter. But more importantly, this distance, so should be compared with this distance. And okay, so this is the tree distance. This is the logarithmic Euclidean distance. Why I claim somehow that they are qualitatively similar. Okay, I mean, I'm sure people know this, but for instance, if you take the leaves of the tree and you embed them on the line graph, on the interval from 0 to 2 to the n, then 1/2 log of the tree distance essentially says, how many times I have to go up until from this, from these leaves embedded on the line 0 to 2 to the n, how many times I have to go up until they meet, and that's roughly, or typically roughly, a log of the log of their distance, log of the difference. And so this is roughly a logarithmic of the Euclidean distance under this embedding. And okay, and indeed, if you look at the results of the tree, they look very similar to the results of on the planar domain. Just again, you have to replace log capital N by little n. This is kind of log of the diameter. The constants are slightly different, but otherwise you again get, so this is now the new centering function for the maximum, but otherwise you still get convergence, weak convergence to a randomly shifted Gumbel with a different shift. Okay, and so to summarize, so the idea is that we want to do the plane with new technology, so maybe we can do the plane, do a study, have better or more finer, resolve some open questions concerning the hard-world problem on the plane. But let's do it first on the tree, because the tree is on one end easier, and the second is not that far. For the sake of this problem, it's not that far from the plane. Any questions? Okay. Let me quickly mention some previous results. So there are some results concerning the the asymptotics of this event. Again, now we're back on the tree. We wanted the leaves to be positive. So there are first order results by Chen and He from 2020. They analyze branching random in much more generality, but only have, and give first order results. They kind of do it as you see in a second, it's a large deviation problem, and so they kind of derive a large deviation principle. So they're more interested in this, in the probability of this event. As I mentioned, we're actually more interested in what happens when you condition on this event. In this case, Roy in 2024, okay, so improved that asymptotics by giving an additional term, and okay, more importantly for us, showed that on the tree, if you condition the leaf to be positive, as in the plane, the field lifts to the height of the minimum or the maximum, and but slightly smaller by this quantity with the non-matching constants. This is okay. I'll get to sharper results, so let me not dwell on this. Okay, so let me talk about results. Okay, so again, when I'm interested in what happens on the branching random walk if you condition the fields to be positive, and as a side kind of side effect, asymptotics for its probability. Okay, so the first thing you want to do when you tackle a problem is to generalize the problem. So, okay, why do the positivity event? Let's do the general right tail event. So I want, let me define omega n of u to be the probability that the minimum, sorry, the event that the minimum is larger than its typical value, minus mn is the typical value of the minimum, by u. Particularly if I plug in u equals mn, I get positivity, but I can do any u that I want. Notice that short, so in the end, I'll be interested in this event at values which are as large as mn. Okay, so these are extreme, kind of large deviation values for the right tail event, not just O1. Okay, and let me fix once and for all some notation. So ut is going to be the fractional part of log u of 2, log u on the base of 2. That will kind of pop up everywhere, and I'll call this the log mod 1 or log mod for short. So this will be the log mod of u. So the first result that I want to present is just a sharper asymptotics, or sharp asymptotics for the general right tail that works for u, which could be of order 2 to the n even, or maybe 2 to the square root of n. Certainly of order mn, which is linear in n, which is what we need for the positivity, and that tells you that the probability decays, well, okay, not exactly Gaussian, so you have a log correction, so that's that, and you, okay, and there is some linear term, and this linear has a constant, and this constant is governed by a function that depends only on the log mod of u. Okay, so there is a constant times u, but this constant may fluctuate. Okay, and the rest is little o of u. Okay, and in particular, if you plug in mn, which is what we're after, okay, so recall this is the order of the minimum or the maximum. Let me denote by ln just the flooring of log n on the base of 2. N prime would be n minus ln. Okay, so n minus this many generations. Mn prime is just plugging n prime here, which would give you just mn minus a correction, which is some constant times log n2. So mn prime is just this minus some logarithmic correction. And then if you just, this is just kind of putting it in, specifying the previous theorem. So if you plug mn in the previous theorem, what you get is this asymptotics for the positivity event. Okay, so yeah, up to little o of n. Okay. But as I mentioned, this is just kind of a side effect. Questions? Okay, we're more interested in what happens when you condition on this positivity event, or differently, how does the field achieve this probability? Well, again, this is the mn, ln, and mn prime. From now on, p plus n is going to be the probability conditional of this positivity event, and expectation follows, and then the kind of corresponding expectation. So this is conditional on the leaves being positive. And okay, and it turns out that in order, not a very difficult result, in order for the field to become positive, it actually lifts to height mn prime. Mn prime is this mn minus c0 log n. In a kind of an exponential manner in terms of depth. Okay. And so this is kind of the typical value, the median if you want, of the centering value for all x's up to ln in the first log n generations. And we even have the tails, constants in the exponential. So the lower tail is Gaussian, as a Gaussian, and the upper tail is Gaussian divided by something like log u. So I have a picture in a second. In particular, if you plug mn in place of u, you get that the field in the first. If you look at the generation ln. The mean of the field is this mn prime, and there are again Gaussian fluctuations for the lower tail and upper and sub-Gaussian fluctuations of the right tail. And I think I have a picture. Okay, so that would make it clear. So this is kind of what happens. The field, every particle of this branching random walk lifts to level mn prime, and does this exponentially. An exponential way, and the fluctuations here are order 1. The kind of important thing, aside from this kind of concentration, is that the field does not go all the way to mn. So if you would kind of naively guess, you would say, okay, I want, as in the work by Bolthausen, Deutschel, and Giacomin, you would think, okay, the field wants to have the new minimum positive, so the field can just lift to the height of the minimum, which is mn, and then do whatever, and then let the field evolve as it wants, or let it descendants, or let the subtree be a typical subtree. It turns out that it actually lifts to a smaller height, and this smaller height is by a logarithmic. So this mn prime, as I mentioned, is just this minus a logarithm. And that's kind of sharp up to order 1. So the repulsion is slightly less than by the order of the minimum. What about joint law? So you can also prove that if at two vertices at generation Ln, at the end of this climb, they are almost independent in the sense that the covariance decays exponentially in the graph distance. So, okay. So it roughly looks like this. Again, so all of them should follow this path in a kind of concentrated way. And then here they're almost independent. So maybe one, then the sibling, the brother of some particle, the sister, is dependent, but you know, if you go 3 particles above, they're almost independent of each other, and then each of them. Okay. So that's okay. So these are kind of bounds, and the question is, can you do better than bounds? Can we have a limiting law? And the answer is yes. And I'm going to describe to you the limiting law. So what happens? How does this tree look like? When you condition things, we condition the leaves to be positive. I'm going to discuss asymptotics in law for 2 kind of types of observables. Local observables, by which I mean local neighborhoods of vertices. And okay, local is a little misleading because I will okay, so yeah, so I'll be able to go even up to order n. I mean, the diameter of this, the diameter of the graph is order n. But so okay, so I can go almost, I can have almost the entire graph in my local observable, but this will not include. So by local I mean neighborhoods which which are, you'll see that this will be quantified later, but this will not include, this will not be in the entire graph. So not the entire graph, but quite large neighborhoods. And so this will be local observables, and global observables will be quantities which are measurable with respect to the entirety. And so I'll give you asymptotics for both of them, and I'm going to start with the local ones. Okay, and one kind of technical thing is that, so I'm going to describe to you, for instance, the limiting law of a leaf when you condition the leaf to be positive after you center. And the problem is that this quantity has typically fluctuations which are order n. And I want to tell you the limiting law, tell you that this, this has a limiting, this converges to some limiting law. And so this limiting law would, it tends asymptotically to a limiting law. This asymptotic law would have fluctuations of order n as well. And the problem is that when you're comparing the law of 2 quantities with fluctuations of order n, is that you cannot use the standard Prokhorov metric for weak convergence, because if you think about it for a second, you get if you take a Gaussian with variance n and 1 mean, and another Gaussian, say with 0 mean, and another Gaussian with variance n and 1 million, when n tends to infinity, the Prokhorov distance between the 2 will get to 0. So, for the sake of comparing the law of 2 quantities with diverging fluctuations, it's not good to use. It's meaningless to use the Prokhorov metric, and we're going to use a stronger metric for weak convergence, which is the Wasserstein metric of order p. Let me just remind you what it is. So I'm going to be able to compare two fields on trees. So these are random vectors or random fields. And the Wasserstein distance is WP infinity, the fifth order Wasserstein distance between 2 laws of fields on a tree so we take a coupling of these 2 fields. One has law P1, the other one has law P2, and you are looking at the pith moment of the uniform distance or difference, and you take the infimum over all possible coupling. Okay, so the Wasserstein distance between 2 laws is, okay, I need the best coupling that I can do to couple these 2, so that if I look at the uniform distance between these 2 fields, the supremum distance, this will have a small, so I'm looking at the best possible way to do this with the smallest, by which I mean the smallest pith node. Okay. So if this is small, that means that I can couple this. If I have two fields and this WP infinity is small, that means that there is a coupling such that if I look at the uniform distance between the two fields, this has a very small or small P node. And there's also okay. So I'll need this, and also need the local version of this, by which I mean that this by which I'm just comparing local neighborhoods, and both of these are metrizable, so I'm going to work with a metric. So I have this WP infinity, which is the metric for the Wasserstein, and I'll have WP loc, which is the metric for the local version of this. So saying that if I have two fields and saying that their distance under this metric goes to 0 means that in any local neighborhood, if I just restrict the fields to a neighborhood, this usual WP infinity goes to 0. Is this clear? Okay. So, okay. I have these two kind of strong versions, and now I'm asking myself whether I should, but I think I have plenty of time. Okay. So let me tell you two kind of slightly technical results, and then two maybe more straightforward corollaries. So these two results are kind of required to study or to describe the limiting law of this branching and more condition to be positive. So the first one says that there is a limiting law. So in fact, there is a family of limiting law, P plus delta, indexed by some parameter between 0 and 1, such that if you, let me go to here, if you evaluate, so H plus n is the field condition to be positive. So if you evaluate the field condition to be positive on a subset AN that starts from one vertex at generation Ln, after centering, okay, and you center, of course, then the Wasserstein P infinity distance between this and a field that has this law on AN goes to 0. So put it differently, so after centering, if you evaluate a conditional field on AN starting from a vertex in Ln, it looks like, or it converges, it's asymptotically the same as the field on AN having this law. And okay, what is delta? Well, delta is again the log mod of n. Okay, so the field after centering looks like has this law, but delta may fluctuate and will depend on the mod log of n. Okay? And there is some growth condition on this sequence of test sets that you look, and this is the growth condition, and the more the stronger the topology that you choose, the larger P, somewhat smaller, the kind of more strict the growth condition becomes. So that's one. So that's kind of one general result. Again, I'll show a corollary which would make this somehow simpler. So that tells you that there is a limiting law, and it's called P plus delta. The second tells you how this, it gives information about how this limiting law looks like, and it tells you, again, let me first decipher this for you. So it says if you look at the test set A, and you look at how this field looks like on the test set A, well, it looks like a usual branching random walk, not conditioned on anything, plus a global shift, okay, which I denote by eta plus delta of infinity. again, the field is H plus delta. The limiting law looks like a regular field shifted globally by some dependent quantity, but kind of governed by a scalar. So there's a global shift. And okay, and this distance is bounded by this. And if you take sets for the right choice of sets or the sequence of sets, you can make this go to 0. Okay. So
the delta, that's all about the integer, the fractional part of this.
Right. Yeah, and I'll say something about it in a second. Let me just give you two kind of corollaries of this technical result. Is that okay? So the two corollaries are how does the field look like? You condition to be positive. One next to the end of the climb, next to generation Ln, and the other one is next to the leaf. So, okay, let's start with the first. So next to generation Ln. So if you look at what happens after generation Ln, after the end of this climb to Mn prime, after centering, it looks like exactly this limiting law. So there is a limiting law, which I described in the previous slides. It depends only on the log mod of n. And that's it. So there is a limiting law next to generation Ln, and the convergence takes place in this local version for any, it's in WP infinity for any finite neighborhood of xln. So that's next to the to Ln, next to vertex in Ln, next to the leaves. Okay. If you take a neighborhood of size n over p minus a logarithmic correction, so if p is equal to 1, if you're only interested in the Wasserstein 1 metric, then it's almost the entire tree, it's almost diameter n. It's okay, but okay. If you want higher p, you pay linearly. Then, okay, what this is saying is that if you look at the field, condition to be positive, at a neighborhood of a leaf, neighborhood of diameter or radius, that radius, after subtracting the shift, the topic repulsion, it looks like a regular branching random walk, only with a slightly smaller number of generations, n prime, at the neighborhood around a leaf of that branching random walk, plus a global dependent shift. So again, under the conditioning, after centering by the entropic repulsion, you get branching random walk with slightly smaller generation plus a dependent shift. In particular, this is saying that the conditional law after centering is not that of the original branching random walk. A, because you have a smaller number of generations, and B, because you're having a global shift. And for the case of the planar domain, this is a major open problem. So if you take the planar domain, condition the field to be positive in some subset, it's a major open question to decide whether, okay, so we know that there's this entropic repulsion, the field lifts up. If you subtract the new centering, so if you subtract the new mean, the question is whether you get an honest discrete Gaussian free field or not. And the answer for the tree is that no, you don't get, because you get this okay, additional global shift. However, if you take gradients, then everything is fine, because then this disappears. The gradient of a field with less number of generations is the same as the gradient of the field without in a neighborhood of a leaf. And so, if you look, so the gradients are the same, but the field itself is not. And here's a schematic picture. Let me just show you this. So again, we know that what happens? The field climbs after generation Ln to level Mn prime, and then here the conditional law here looks like shift Mn prime plus a limiting law that depends only on the mod log of n. And next to the leaves, if you look at the neighborhood which is not too big, then it's Mn prime, it's the Mn prime plus a branching random walk with a slightly smaller number of generations plus a global dependent shift. Any questions?
The shift is random?
Shift? Which shift?
And the eta have...
Yeah, it's random. Yeah, this is certainly random. So random, you can describe the law, but yeah, okay. And it depends. It has all moments, yeah, it's well behaved. Certainly random. Okay, in particular, this nails the sorry. This, okay, so in particular, we get the mean, that the mean at the leaves is mn prime plus a constant that again may depend on the log, on the mod log mod, plus little o of 1. Okay, so we know precisely the mean under the conditioning, and again, the important thing is that it's not, the shift is slightly smaller than smaller by logarithmic factor, by diverging factor than the order of the minimum. Okay, one comment about this log mod is that it's not clear whether it's really there or not. So whether, for instance, this law depends on so it comes up in the proof, but maybe all these, maybe the limiting law, this p plus delta, does not depend on delta. We don't know that. And we also do not know, so all the constants here that depends on delta, we don't know anything, whether they're continuous, whether they have periodic boundary conditions, and so on. And so I don't know, yeah.
So does it, I remember from Darmstadt, so yeah. Does it arise because of the discrete structure of the
right. Yeah.
If you had like a Poisson...
one has to be careful with all of this kind of thing. So yeah, so this comes out, okay, so this kind of question translates into whether somehow the discreteness of the model, this model is discrete because you have discrete generations, and the question is, well, whether this discreteness somehow survives in the limit. It's kind of a complicated question of how to get rid of this discreteness in such a way that would not affect I mean, if you add exponential clocks, then maybe the best way is just not to have branching at all. And branching random walk would, branching Brownian motion, or if you add branching Brownian motion would behave very differently. If you want the branching Brownian motion to be positive, you just don't branch. So here you cannot do that. So, okay. Okay. Let me switch to global observables. So global observables would be quantities depend on the whole tree, like global maximum, minimum, exponential additive martingales, and so on. And here are some results of that nature. So if you look, for instance, at the population mean under the conditional measure, then this converges to the mean, to some quantity, to mn prime plus a fluctuating constant. And so once you condition the field to be positive, the population mean converges to a constant. And if you look at the unconditional case, the population mean is random, determined by the first generations. And so you get this difference, so you get convergence to a deterministic value, not random. Similarly, you can ask what's the new maximum. So now I condition the field to be positive, I have this topic repulsion by mn prime. What's the new maximum? Turns out that you can show, okay, so you can show that the maximum of the conditional field is still Gumbel, but you lose the random shift. Okay, so you still have reconvergence of the maximum after subtraction of a centering value, but no more random shift. And moreover, this mn, okay, the centering value is, okay, this is the centering value, and it's different than what you perhaps guess. So one guess for the new centering value is this mn prime. So if it lifts to mn prime, maybe it's going to be mn prime plus mn prime, the new centering value, and it's bigger than that. And okay, maybe a more natural guess is that it's mn prime plus mn, the usual order of the maximum. but it's actually smaller than that, and it's this quantity. Okay, the minimum is also very different. I mean, the minimum, of course, cannot be, so in the unconstrained case, it's just minus mn plus the randomly shifted Gumbel. Of course, here it has to be positive, so it cannot be that, and in fact, it actually converges to an exponential times 1 over n. So after multiplying by n, and again, some constant that may depend on the log mod, you get exponential. So it's 1 over n times an exponential. And okay, derivative, it's not derivative, sorry, additive martingales. If you look at the subcritical ones, so again, if you look at the subcritical, kind of the Gaussian multiplicative, the subcritical Gaussian multiplicative chaos, the total mass in the unconditional case converges to a random quantity. Here it converges, okay, this is what you have to do. I mean, you subtract the new mean. The analog in the case of the conditional walk is okay, converges to a constant. So you lose a lot of the randomness, a lot of the kind of randomness in the beginning, and if I have time, I'll explain this. Or if you ask me a question, I'll explain this. Okay, so I have until 12?
Yes.
Okay, so yeah, so again, a schematic picture. This is false. This should be just mn plus, not the mn prime here. And so the new maximum is mn plus. Okay, so these are the results. Okay, in particular, there's no shift. Okay, under which the conditional field. So there's no recentering under which the conditional field and the unconditional field would be. So the what this is saying is that they're mutually singular with respect to each other in the limit, regardless, regardless of any centering that you can decide. Let me tell you some of the proofs, if there are any questions, if there are no questions. Okay. So how do you prove? Okay, now I'm going to kind of explain perhaps the less interesting part of the proof, but it does give you at least the reason for why you have, for why the shift is not mn, but rather mn prime. So why, when you lift up, you lift to a slightly lower level than the height of the unconstrained minimum. Okay, so again, we want to understand this right tail event of the minimum. And okay, so you start to think, okay, how do I realize this event? How do I make the minimum larger by u? Well, I better, kind of the strategy would, natural strategy is to have all particles up to some generation go above u, and then let the field have all particles at generation k above u. Then I can essentially let the field more or less evolve as it wants, because I've already lifted the minimum by u. And then there's a trade-off, because well, if I don't do it, then I start playing exponent. If I have too many particles, so let me say this. Let me rephrase that. There's a trade-off between which generation you want to do this. On one hand, you want to do it as quickly as possible, because in the beginning you have less particles than later, so you want the smallest generation. So you want to lift them to level u, the smallest possible generation. On the other hand, if you do it, the more you wait, the more steps are accumulated, and so the variance is larger, and so it's easier to actually push them above u. And so the question is, what's the right k to do it? Okay. And then you look at the Hamiltonian. So if you look at the Gibbs gradient description that I gave you before, so this density, the expression for the density, so this appeared in the exponential with a minus sign. And okay, and I want, so my field starts, okay, so that's kind of the exponential cost that I pay for a trajectory f of the field. And the field starts from 0, and I want to have it a generation k and on, say. to be u. And now the question is, suppose that I decide that I want the field to be at level u generation k. What is the exponential costs? So what is the optimal exponential cost that I can have for a function that starts from 0 and reaches u generation lk. Okay, and it turns out, okay, so that would give me at least on the exponential scale, what's the cost of lifting the field from 0 to u at generation lk. So again, if I kind of disregard entropy terms. And okay, it turns out that the best way to go from 0 to u and minimize this Dirichlet energy is take the harmonic interpolation between 0 and u. And so this is this u, which I call u uk. That's the harmonic extension from 0 at the root to u at the leaves lk. And this expression is precisely, so this is precisely this capacity, this is the tree version of the capacity that I talked about before. Again, this is homogeneous, so this would be u squared. I can take the u out as a u squared, because of the square here, and have a 1 here, and then I get the minimal Dirichlet energy for a function that goes from 0 at the root to 1 at the leaves, and that's precisely the discrete version of this capacity that I mentioned before. So this is why this capacity is kind of popping up. But anyway, okay, that's an anecdote. It's for us. In any case, I'm interested. Okay, so the optimal way to get from 0 to u, a generation lk, is to take the harmonic extension, the harmonic interpolation. Okay, and then you start. Okay, and that's kind of very easy on the tree. It's very easy to construct this harmonic extension explicitly, just by random walk on the tree estimates. And then let me look at two cases. So k is a generation where I have the field at u already. So if I do it after log to u many generations, flow of log to u, it has to be an integer, then indeed the harmonic extension looks like okay. That looks like okay, so the harmonic function goes exponentially to u, and this and the Dirichlet energy, the cost of doing this is 1/2 u squared plus order u, and that's regardless of k. So if you increase k, well, you might be able, to save a little in this order of u. But in any case, we're going to incur other error terms or other costs which are going to be exponential in u. So I don't really care. So for my purposes, or the purpose of this precision, going above log to u is not going to help us. On the other hand, if you go if you raise the field to level u at generation k for k, which is smaller than this, you actually help this 1/2. You can write the harmonic extension, but if you look at the Dirichlet energy, you actually help this 1/2 u squared by something that's superlinear in u. So for instance, if I just do it in the first generation, if I lift the field to level u in the first generation, then I have to control two edges. Each of them is Gaussian, each of them costs me 1/2 u squared. I have two of them, so it's u squared. So if k is equal to 1, if I lift the field to level u already in the first generation, it costs me u squared, not 1/2 u squared. Okay, so it's certainly not worthwhile to do it, at least on an exponential scale, before log to u. Okay, and that's that's just a kind of motivation for choosing log to u. And so indeed, this is the right time to do it, the right generation. So you lift the field to generation log you lift the field to height u at generation log 2 of u. So that's this is LU. Okay, and then comes kind of the realization that in fact you don't need to go all the way to u, because once you've weighted log 2u many generations, the remaining subtrees already have smaller, less many generations. And so the minimum is kind of automatically increased for you from minus mn to minus mn minus lu. And this difference is actually a constant lu. And so, so by the time you reached the level u, you've already automatically gained C0 Lu, and that realization makes you, okay, and because that realization, you understand that you actually don't need to go all the way up to u, you can actually go to u prime, which is u minus C0 Lu. And that really explains why the lift is smaller than mn, because by the topic repulsion order is smaller than mn, because then, if I have it in the next slide, so then actually you raise the field not to u but to u prime, and this is kind of the optimal profile and optimal the minimal energy. And then if you plug in mn, the hard roll problem, then you get this Lu becomes log 2n, and this u prime becomes this mn prime. Okay? So the reason that you need, maybe the take-home message, is that the reason that you need, that actually the atopic repulsion is of smaller order than the size of the minimum. In the case of the branching random walk, in the case of planar domain, it's going to be slightly different. It's going to be different. But for the tree, the reason that, turns out that the only reason that, the difference, the reason that you can raise the field to a slightly smaller level is just because that by the time you get to the right, to the level mn, you've already automatically increased the minimum because the number of generations have decreased. And I think, okay, then you need to kind of, make this into a proof, which I'm not going to tell you, but in the end you can actually, make this into a proof of the right tail. And I guess